Hello everyone, thank you for attending our presentation. My name is Guo An. I'm a PhD student from Nanjing University in China, and today I will present our ASE2024 paper on autonomous driving testing. Its title is SoVAR, Building Generalizable Scenarios from Accident Reports for Autonomous Driving Testing. This research is a collaborative effort between Nanjing University and Nanyang Technological University. Let's get into the background. The development of autonomous vehicles has achieved tremendous achievement over the past decade. However, recently reported data on fatal accidents involving ADS suggests that the desired level of safety has not been achieved. For instance, self-driving Uber killed a pedestrian in Arizona in 2018. So, there is a growing need for comprehensive testing approaches to ensure safe driving. We designed a tool for automatically generating road generalizable scenarios from accident reports. Generate road generalizable scenarios from accident reports has two challenges. First, NLP tools do not exhibit good performance due to the inclusion of traffic jargon and non-standard phrase structures in accident report. Challenge 2 is that the map covers all the key static properties of complex roads, including road type and road size. It is extremely difficult to find roads that fully match the extracted information when producing the scenario within the map to be tested. Besides, it is necessary to test multiple roads on the map because collisions often occur in similar road environments, thereby challenging the ability to adapt to a specific map. This is a motivating example of challenge 2. As shown in figure, the accident that occurred in subfigure A can also occur on the road in subfigure 1B. However, directly reconstructing the original trajectory on the right road cannot replay the accident. The vehicle turns left along the fixed trajectory P to the road R1 with a width of L. When the road width becomes 2L, the vehicle turns left along the same trajectory P to the reverse road R2 with a width of 2L. It is inconsistent with the expected trajectory P prime and alter the semantics of the accident scenario. Next, we introduce the general framework called SoVAR. SoVAR consists of three steps to obtain simulation-based tests. SoVAR initially abstracts the accident scenario into layers. It then leverages an LLM to systematically extract information about accident influencing factors from the accident report, organizing the information layer by layer. Following this, SoVAR established constraints on the pre-accident driving actions of traffic participants and employs a constraint solver to generate trajectories that comply with the specific constraints outlined in the accident report. Subsequently, the trajectories generated along with the extracted environments and road information are inputted into the driving simulator to reconstruct the car accident scenario. Finally, in the evaluation phase, SoVAR converts the generated simulation scenarios into test cases that include test oracles. These test cases are then inputted into the ADS. SoVAR checked whether the ADS under test successfully reaches its final expected position without encountering any crashes. For step 1, SoVAR divides the extracted information into three layers: road, environment, and dynamic objects. SoVAR extracts accident information layer by layer using the prompt patterns designed in Table 1. For each linguistic pattern, it first explains the meaning of each attribute to help LLM understand the extracted information. Additionally, the pattern includes heuristic rules to guide LLM in producing accurate results. For example, if a car intended to perform a certain action, but the collision occurs before the action is executed, the intended driving actions should not be extracted. For step 2, SoVAR generates trajectories that comply with the specific constraints. We design 5 group constraints to describe accidents. We considered the basic driving actions and the combination of basic driving actions. As shown in figure, the collision takes place at the regulated intersection. A blue vehicle is observed traveling northbound in lane L3, making a left turn under the circular green signal, while the green vehicle is traveling south in lane L5. During the blue vehicle's left turn, its front collided with the front of the green vehicle. This example can be described by 5 groups of constraints. All constraints can be found in our open source link. Take left turn as an example. As shown in figure, SI plus 1 represent the direction vector composed of the position of the ith waypoint and the position of the I plus 1th waypoint. The vector SI plus 2 represents the right normal vector formed by the position of ith and I plus 2th waypoints. We use a constraint solver to solve the above constraints. For the final step, SoVAR converts the generated simulation scenarios into test cases. SoVAR put the extracted environment conditions and planning trajectories in the simulator. Then, SoVAR automatically derives systems-level test cases from the output of the trajectory planning model, allowing the ego car to choose a trajectory different from the one described in the accident report to avoid collisions. If a collision occurs, it may be due to a decision error by the autonomous driving system. We designed 3 research questions. RQ1 is about information extraction. How effective is information extraction from accident reports with SoVAR? RQ2 is about generalizable generation effect. What is the effectiveness of SoVAR in producing generalizable simulations with the intended impact? RQ3 is about crash detection. To test derived from generalizable scenarios find crashes in autonomous driving systems. We use the industrial-grade autonomous driving system of Apollo, GPT-4 large language models, and the NHTSA dataset. Next, we propose using the scenario reconstruction rate metric to measure the effectiveness of SoVAR in reconstructing scenarios from accident reports. For RQ1, Table 2 illustrates the accuracy of various methods for extracting information from accident reports. We observe that SoVAR and ASE3R exhibit higher accuracy in extracting straightforward information, such as speed limit from accident report. However, they demonstrate relative lower effectiveness in extracting complex driving actions with contextual dependencies. For AQ2, Table 3 shows the number of successfully reconstructed scenarios and SRR metrics and their different road types. The average SRR of accidents occurring at intersections, T-junction roads and straight roads are 93%, 72%, and 82% respectively. These results demonstrate that, in comparison to ASE3R, SoVAR is more capable of generating generalizable scenarios. For AQ3, here the table represents the number of collisions caused by self-driving cars in generated test scenarios using different methods. We present 4 safety violation scenario types as shown in figure. In addition, as shown in slide, we summarize another 2 types of collisions, which are caused by irregular NPC actions. Although in these cases the NPC violate traffic rules, we believe the ADS should have emergency avoidance capabilities when there is sufficient time to react. In such scenarios, the ADS's ability to issue early warning and take countermeasures is crucial to ensure safety. In summary, the contribution of our research work comes from 2 parts: accident reconstruction and autonomous driving system testing. For the accident reconstruction part, SoVAR enhances LLM's test comprehension and parsing capabilities through prompts and generates accident-related trajectories by solving a predefined set of trajectory specifications. For the autonomous driving testing part, SoVAR converts the generated simulation scenarios into test cases. Our codes are available. That's all for our presentation. Thank you for your attention.